So in the last class I started talking about statics of rigid bodies. I was saying that when I talk about RB statics, I am interested in knowing the relationships, the non-trivial relationships that would exist between different forces of the force system that is acting on the RB. The RB itself is at rest, but it is in the state of rest because of the presence of certain forces, right? The relationship between those forces will be decided by the Euler's two axioms. Euler's first axiom will tell me that the net force acting on the RB must be zero, and the second Euler's axiom, or rather the modified Euler's second axiom, would tell me that moment of all the external forces acting on the RB about any point A must be zero, about any point A, no restriction on point A at all. This is true for a general three-dimensional force system acting on the RB. Now in some cases the RB will be under the influence of a planar external force system, planar. And suppose that plane in which all these forces are lying, they are in this plane, or rather that plane I call the plane of x ex y ey. So a body, an RB which is in static equilibrium under the action, under the influence of a planar external force system, will have three non-trivial scalar equations. The net force in the x direction would be zero, the net force in the y direction would be zero, and the moment due to all forces about a point A which lies in that plane, which plane? This plane, will have a z component 0. Again, it's same Euler's first and second axioms. But here I have only three scalar equations. So every RB will come with its own three scalar equations. For a general three-dimensional force system, every RB comes with its own 6 scalar equations. And those equations can reveal the relationship that would exist between different forces. And those relationships we want to know for in various problems of interest, whether they are toy problems of our course or the problems in real life. We want to know that those relationships between the forces. Then I was talking about a two-force body or a two-force member, acronymed TFM. And I said that a two-force member is an RB which has exactly two forces acting on it at two different points. And except for those two forces, there is nothing else. No other torque, of course, no other force. I gave some examples. If you draw the free body diagram of an RB in this way, at one point there are two forces, Fa prime and Fa double prime. I would not call this as a two-force member. Then I gave this example in which I had a point B where Fb is acting, and then at point A in my FBD I am putting two forces, Fa prime and Fa double prime. This is also not a two-force member. There are three forces acting. However, if you combine these two forces, and then you decide to draw the free body diagram as what I have here, in which at point A now you have put a force Fa, which is Fa prime and Fa double prime. You add these two together and then you find the vector sum of that force and go ahead and put that force on the FBD. Then it is indeed a two force member. Okay, such is the definition of two force member. Why do I worry about identifying and calling a member as two force member? It will become clear in a little while. I gave another example in which I have an RB. Indeed, there are 2 points A and B where two forces are acting, Fa and Fb, but then there is a torque also acting on it. By my definition, I would not call this either a two force member. This is not a two force member either. Okay. So I hope with these 3 examples it is clear what we mean by a two force member. Now comes the question, why am I worrying about defining such a two force member? Consider a two force member like this. Now in general it can be in static equilibrium or not. I mean, in general it may be in static equilibrium or it may not be in static equilibrium. However, if we know for sure, if we know a two force member is in static equilibrium, a very interesting relationship follows. Relationship of what? Relationship between Fa and Fb. So if it is in static equilibrium, Euler's first axiom will give me Fa plus Fb equals 0. Has to be. These two forces must be equal and must be directed opposite to each other. But that is not all. If it is in static equilibrium, then there must exist one more relationship, one more vector relationship between the two forces, and that comes from MESA. And that would be something like this. Actually, this relationship exists, MA equals 0, or so these are points A and B. I could have taken any point here, MT, MN, MQ, MR, whatever you want to take, you can take. Whatever. Net moment due to all the forces about any point in space must be 0. Without any loss of generality, I have taken that point to be A. Nobody stops me from taking this point to be A. Now see, once you take this point to be A, this equation implies that RAA cross FA, this is the moment due to force FA about point A, and then there is the other force FB acting at point B. This must be 0. But this is 0 anyway. On its own it is 0. It means RBA cross FB must be 0. This implies that RBA must be parallel to FB. Right? And then I already know that FA, whatever is the direction of FB, FA will be opposite to that, right? So you combine 1 and 2, conclusions 1 and 2. Conclusions 1 and 2 lead me to one of the two possibilities. There are only two possibilities here now. This is the first possibility. This is the other possibility. These are the only two non-trivial possibilities. Of course, there is this third possibility which is trivial, that FA and FB both are 0. I am not even thinking about that trivial possibility, because if FA and FB are 0 to begin with and the body is at rest, why would I go and waste my time doing any analysis? It's a trivial case. Okay. So the moment now onwards, if you are given a body or a set of bodies which is at rest, and if you are able to see a rigid body which is a two force member, and you know that this set of bodies is at rest, then you don't have to worry about knowing the direction of these two forces. The direction of those two forces will be either like this or this. Like this or this means what? These forces are pointing towards each other and are along the line connecting A and B, or they are directed away from each other, but they have a common line of action, and that common line of action is nothing but this vector RBA itself. RBA is the line of action. Okay. And you also know that FA magnitude is equal to FB. This much you know already. Now what actually is the magnitude of FA and FB? That could be anything. For that you will have to solve the full problem. But at least you know the lines of action of the two forces if you are dealing with a two force member. That is why I defined, to have this convenience of concluding this or this by visual inspection itself, I identify or I introduce this concept of two force member. Okay. if you have a rigid body which is straight RB, if the member is straight, it is a two force member, then there are only two possibilities, this or this. So for a straight member, the forces, the line of action of the forces is nothing but the body itself. I mean the line connecting the body, line connecting the 2 points on the body. Okay. In this case, we say that the member is in tension. Okay. Member is in tension. It is being pulled from both the sides. In this case, we will say the member is in compression. So today is the last lecture session, and my attempt today is to cover 2-3 topics in static equilibrium. Again, I will not be able to cover all the topics which I normally cover in a regular semester, but 2 or 3 topics we still have time, and that's what I'm going to do. So this was one of those topics, two force member. The next one is friction. Now friction force we are familiar with. We know friction force is generated by a normal reaction, corresponding normal reaction. There is coefficient of static friction, coefficient of kinetic friction. We are aware of these concepts. In fact, while dealing with kinematics and even dynamics, we were using these ideas. In statics also, friction is important. So let's quickly review these different coefficients of friction. And then I will introduce you to a new topic. I believe it would be new for you, and that is belt friction or rope friction. Okay. So consider a mass which is kept here on a surface which has friction, and you are applying a force P on this. In your lab you have set it up. You are trying to do an experiment. The FBD of this body would be will have a normal force, its weight P acting on it, and then there will be a friction force. Right? Now you start this experiment with a very small force P. Okay. And you want to estimate what friction force this object is experiencing. So on this axis I plot P, It's a lab experiment. We know F will be something like this, where mu effective can either be mu k, or it can be mu s, or it can be something less than mu s. Now mind you, these quantities mu k and mu s, they are characteristic of the two surfaces involved. So they are like known constants. But the way I am posing my problem, I am saying that friction force can be written as a constant, a factor, I should say a factor, non-dimensional factor times normal reaction. And normal reaction in this case we know is W. So how will this graph be? When you don't apply any force P, the friction force will be 0. And then you gradually start increasing the force. You will get a curve like this. Okay. And at one point, what will happen is that when you reach mu s times n, this is coefficient of kinetic friction. At mu s, when the friction force reaches mu sn, and if you still increase P, what will happen? The object will start moving, and then this friction force will suddenly drop, and at this point the friction force will be mu k times n, right? Mu k we know is less than mu s. So at this point we say that the motion is impending, motion is about to happen. Right? Motion is impending. Whereas over this region, I can write over this region friction force is mu effective times n, where mu effective is less than or equal to mu s. Motion is not impending. If motion is not impending, mu effective will be something less than mu s. When motion is impending, mu effective will become exactly equal to mu s. And here relative motion happening mu effective will be equal to mu k. Okay, so the idea is to write the expression of the friction force in a general way a factor times n. That factor we call as mu effective, and what the value of that factor mu effective is, that will depend on what is happening to the body. If motion is impending, as I wrote, it will become motion is impending, it will mu effective will take the value of mu s. Motion is not impending, then mu effective will be something not known exactly, but I know it will be less than mu s, and when there is relative motion, mu effective will become mu k. So now use this quantity mu effective. Let's talk about belt friction or rope friction. Consider this pulley which is stationary, and we have tied a rope around it the way I have shown, this yellow color. The rope is fixed on one side to the ground, tied there, and on the other side we have tied a mass which is hanging, and there is gravity present. The tension on the two sides of the rope I am writing as the tension values as T1 and T2. Now if friction is absent, then we take T1 equals T2. That's how we solve again problems in class 12th. We always say that the rope and the pulley are frictionless and we match the tension. But now what will be T1 by T2? Whether it will be 1 or not equal to 1. One may expect that it is going to be not equal to 1, fine. But what is the relationship? If there is any relationship between T1 and T2. That is what I want to derive now. I will still continue with this assumption that whatever, whether it's a belt or a rope or a cable, it is still massless. In class 12th you make both the assumptions. You say that the rope is massless and there is no friction. I am removing one constraint, there is friction, but I am still assuming that the belt or the rope is massless. And here I have a situation where a stationary pulley is there, and there is a belt or a rope shown in yellow color here, which is wrapped on the pulley. But it is not wrapped completely over 360 degrees. It is wrapped only over a particular angle, beta, which is less than 360 degrees. It's not full wrapping. And then I have drawn tension values, tension symbols I have written on the two sides of the belt, T1 and T2. Okay. And again, intent is to find the relationship between T2 and T1. Now to find that relationship, what I am going to do is to focus on this much length of the belt or the rope. Okay, delta theta. So I go to an angle theta, which is finite, and take an infinitesimal increment in that angle. I get a sector on the pulley. Corresponding to that sector, I get this arc length, which is r delta theta. and I bring that length of the belt here, and now I will try to draw the free body diagram of this part of the belt. And my hope is that with this I will be able to find relationship between T1 and T2 eventually. Let's see how it happens. Okay, so this delta theta is the sector that I identified here, and then what I'm drawing a line which bisects this angle, both sides, delta theta by 2, both sides. Okay, this direction is EY, which is radially out direction, or you can call that normal to the pulley surface. Okay, and then perpendicular to that I identify EX. So 2 unit vectors. This will make the working coordinate system for me. Now I have taken an arc on the belt, and on the two sides of the belt, since I have cut the belt into the small, since I have taken a part of the belt cut out from the full belt, and I want to draw the free body diagram, I must put the tension force that the left part must be exerting on this r delta theta length. I am putting that tension force as T, and on the other side I put this force as T plus delta theta, T plus delta T. I expect there may be some increment in tension after all. Again, if friction force is 0, the sides it will be T, but since there is friction force, I am expecting that on one side it is T, the other side it is T plus delta T. Now notice that this tension force, the arrow, is inclined to EX at this angle delta theta by 2, and similarly this angle is delta theta by 2. You can check the geometry, it will turn out to be like this. Okay, so I have four equal angles denoted as delta theta by 2. One is this angle, the other is this, third is this, and the fourth is this. Okay, what other forces are acting on this? I will put a force here, delta N, normal reaction force. Normal reaction force exerted by the pulley surface on the belt, delta N. Okay, what other force we should put? Other force is delta F, which is the friction force. Delta F is the friction force. Drawn from right to left. So as there is more tension force on the right side, I expect the friction force to be going from right to left. On what? On the belt. This is the free body diagram of the belt. Of course, on the pulley surface it will be in the opposite direction, but on the belt it will be from right to left. On belt arc, not the entire belt, but the belt arc. That belt arc is this part, what I have shown. So there are four forces acting on this body: T plus delta T, T, delta N, and delta F. I have assumed the belt to be massless. If not, you will have to put the mass also, but I am not bothered about the mass. Now let's try to find the relationship between these forces. Along EY direction, force relationship. So I have delta N along positive EY direction, and then I have component of T here, this T. In the vertical direction, what will be that? T sine delta theta by 2 along minus EY direction. Okay, and then I will have T plus delta T contribution again along minus EY direction. This must be equal to what? Mass of belt, mass of the belt arc times acceleration of cm of belt arc. But mass of the belt arc is 0, so it means that I actually get this relationship. So I call as equation number 1. I can write another force relationship along EX direction. What is happening along the EX direction? This T plus delta T will have a component along EX, and that would be cosine delta theta by 2. And then this T here will have a contribution along minus EX direction. So I put this. Friction force is along minus EX direction. I have delta F. Okay. And at this point I would like to write this delta F as mu effective times delta N. This is where I am using this new factor, mu effective. And the moment I use mu effective, what I am essentially ensuring is that this derivation is applicable over this entire regime. Everywhere it is applicable. If I use friction force with mu effective times normal reaction, it is applicable everywhere. If I know the motion is impending, here you will put mu effective as mu s. If it is here, if there is a relative motion between the pulley and the rope, in that case also that derivation is going to hold good. The only thing you have to make sure is mu effective is this. And if the motion is not impending, you are operating in this zone, then also you can use the derived relationship with mu effective as something which will be less than mu s, and there may be other ways to find it, but the expression will still hold good. So these are the forces that are acting on that belt arc in the plus Ex direction, and that should be equal to again mass of belt arc multiplied by acceleration along Ex, just like it was along Ey here. Okay, but again doesn't matter because mass of the belt I am assuming to be 0. So I have two relationships, one is this and the other is this. Okay, I call this equation number 2. Now let us eliminate delta n from 1 and 2. 1 has delta n here and 2 has delta n here when you replace delta f by mu effective delta n. I am going to eliminate delta n so that I get a value of delta t. That's what I am actually interested in finding. Okay. Now if you eliminate delta n from the last two equations, leaving this as a homework for you, I'm skipping 2-3 steps, you will get a relationship which is delta t by delta theta I would like to write one more step to make it easy for you. By delta theta. After eliminating, you divide the entire equation by delta theta. That will lead to this relationship which I have written. Okay. Now I am going to take limit of delta theta going to 0 on both sides. Okay. What does it mean? You go back to my diagram here. I am taking this arc length to be as small as possible. Okay. I am letting this delta theta go to 0, which is a legitimate limit to look at. What happens? So here I have sine delta theta by 2 by delta theta by 2. Now as delta theta goes to 0, your cos delta theta by 2 will tend to 1. Delta t can be written as dt d theta in the language of calculus, and on the right hand side, of course, t plus delta t by 2 will tend towards t, talking about this factor, and then sine delta theta by 2 divided by delta theta by 2, this will become 1. So I get a simplified expression which is dt theta. If you change that angle theta from to theta plus something small increment, the resulting increment in tension is dt. That becomes equal to mu effective times t. It's a nice looking expression. But recall, my actual intent was, my primary intent was to relate T1 and T2. How do I get a relationship between T2 and T1 at the ends of the belt? I can get that by integrating this equation from theta equals 0 to theta equals beta. What is beta? Beta is the total angle. You see, beta is the angle that tells me how much is the interacting surface. Right? From here to here. So it is the angular extent of the interacting surface between, or the interacting surfaces of the belt and the put. That is the limit of my integration. And here I start theta equals 0 and this becomes theta equals beta. I come here. Okay. So this is the integration. And what would be the limit on the right hand side? Before integrating, let's bring in this form. That will make the integration very easy. Let's write it like this. And when I say integrate LHS, RHS, I mean this. So I have integration of this d theta, where theta, as I said earlier, goes from 0 to beta. And what is the range of t? What should I put as the limits? T1 and T2. Right? As theta goes from 0 to beta, tension goes from T1 to T2. What do I get? This is the relationship between two sides, tension two sides of the belt. T2 by T1 x goes as exponential e raised to the power mu effective times beta. Now mind you, beta in this derivation is in radians, not in degrees. When did I assume the beta to be in radians? Here. This thing will go to 1 only, and then theta or delta theta is in radian. Anywhere else? No, I think that's the place. Because of this step, we have committed ourselves to the choice of putting beta in radians. Be careful about this when you are using the relationship to solve any problems. In the problem statement, beta may be 60 degrees, 40 degrees. If you put that here directly, you won't get the right answer. Okay. Now if I draw the free body diagram of the entire belt length, on this side you will put T2, this side you will put T1, and then the normal reaction force will be a distributed force system. Normal reaction force. Normal reaction force. Distributed. Okay. In fact, to be precise, if this surface was circular, then all these arrows will be converging to the same place. Radially out, that's the word. Radially out. Okay. Friction force must be acting on the belt. Which direction will it be acting? Friction force will be acting in this direction. Friction force distributed. That also is distributed. Okay. Note that T2 will be more than T1. T2 will turn out to be more than T1 according to this relationship. So if you look at this figure, on the belt, if the friction is clockwise, friction is acting actually counterclockwise, then T will be increasing clockwise, opposite. Tension increases from left to right. Friction force on the belt acts from right to left. Now, if you draw the FBD of the pulley, of course its weight will be acting at its own center. Okay. What other force? Normal reaction from the belt on the pulley surface. And then friction force, how will that be acting? On the pulley, the friction force due to the belt will be clockwise. Right? Newton's third law. Where is tension acting on the pulley? Should I draw tension forces on the pulley? I know I can't hear your response, but I want you to think about it. Should I draw any tension force on the FBD of the pulley? Should I put any tension force on the FBD of the pulley? The answer is no. Pulley does not experience any tension force actually. The only way pulley knows that a belt is lying on its head or around its neck is because of the normal reaction force and the friction force. I have drawn them all. So there is no need to put T1, T2. T1, T2 are the forces that are acting on the belt. They appear here, they don't appear here. Alright. Okay. Now after all this monotonous derivation, let's have a look at this picture. Looks interesting. At least to me it looks interesting. This is from Baer and Johnston's book. And this picture seems like it has been taken in some port area. It seems like there is a big boat on this side, and this rope is tied to that boat. Okay, so the tension in this side is T2, and since it is connected to a boat, maybe boat is trying to drift away because of waves in the sea, and that would be a massive force, because typically these cargo boats are huge. And this man has taken upon this task to stop that boat from drifting away. But he has not that much. He cannot generate T2 on his own, his muscle. I mean, whatever is the strength of the person, he cannot generate, his hand muscles cannot generate a tension which can be comparable to T2. He can't hold the boat directly, tying the boat to a rope and holding that rope directly. What is he doing? He has wrapped this rope multiple times over this body, which is like a fixed pulley. And as he wraps it multiple times, he gets this exponential magnifying power, what we derived here. so that only he generates a small T1 with his muscle power, but actually friction helps him create a big T2 which can hold the boat from drifting away. To be precise, if we try to gauge what is the value of beta in this case, to me it appears it is 6 pi. He has wrapped it 3 times, 3 times 2 pi, right? Looks like 1, 2 and 3. 3 wraps. So with a small T1, he can stop the big boat from drifting away. If even more T2 is required, all he needs to put is one more wrap. Again magnifying, exponential magnifying power of 2 beta, 2 pi every time he gets. Alright, so friction at work, belt friction at work. Alright, so we are done with this topic. We take a break. We meet at 15 past 70, 5:50.